Hello, welcome back to BLENDERSUSHI Live Noding. In this episode, I'm going to share with you one of my setup using Sverchok to generate this kind of I call it like a random walk. I did like an older video of a similar kind of concept of random walk, but I want to kind of look at it again, but and I'm doing it in different kind of way, different setup, and I believe this is a lot more simple, and I will try to explain it how I come to generate this kind of setup. So basically what we have here is some kind of something that starts from 000, just a single point, and I'm kind of accumulating like the points vectors in all random points. Yeah, it sounds like a little bit hard to understand, but I'll show you how I get to this point. Basically, the idea came when I was studying this book called Think Python 2, and there is one chapter where the example is using this turtle module in Python. With a turtle module, you are able to draw some kind of it's like a 2D kind of tracing of a turtle object. And if you look at the documentations for the turtle module, you can see like some examples and all the functions that you can do using the turtle. I'll show you real quick what's the turtle module looks like in Python. We're gonna close Safari first, and then soon I'll go back to Blender. So I'm using this Pineapple, just the prettier version of Jupyter Notebook for interactive Python. Anyhow, I'm using the turtle module here, and I'll create an object. I call it I'll put it inside a variable called Bob. So I'm creating a turtle object. If this is like a node in Blender using Sverchok, the object that we just created is probably like a single node. That's how I kind of think of it. And if I try to draw a letter S, this is what I do. This is just importing the turtle object. We don't need to do that. We already done it up here. So what I want to do is just to draw the turtle. It's gonna be like at the original position, and I'm gonna move this turtle named Bob, move it forward in 100 unit, and then turn it left. The turtle's gonna turn 90 degree to the left, and it's gonna move forward and then turn left again 90 degree, and then move forward and then turn right 90 degree, and so on and so on. This is like the whole procedure. So that's the result I'm getting. The turtle is represented as a single arrow there. I'll do it again. Oh, actually, what happening is the turtle keep the last position and kind of keep going. I can actually clear the image by resetting the screen. So there you go. So that's the turtle is drawing it in 2D. And from the last position, I can kind of move it 10, do it again, do it again. This is a nice thing about in Jupyter Notebook. You can do this quite easily, and then you can try other things like making a square. And then here, I'm following that book, Think Python book. They have this example how you can generate like a square, and you also make some kind of loop, and or this one is actually drawing square twice with different size, and then you can also make like a, I believe like a circle or something. This is like another example where the turtle just keep going in the loop for how many times? 4 times. Or actually this one keep doing it for how many seconds is this? For I in range 1, 100, 5, So it is probably gonna draw the square 20 times. So this is the kind of thing that I want to try to simulate in Sverchok, or basically the same concept. You can also draw a circle, I think. So this is actually more like n poly. There's some kind of similarity how you do this using functions in Sverchok. But the nice thing about Sverchok is, of course, you already have a lot of functions and nodes for you that's enable you to draw n poly or circles. So you don't need to think about all this function. But this is all this can be translated into Python script nodes in Sverchok if you like to do it from scratch, and you definitely will learn something if you're doing it that way. So let's go back to this thing. So I'll explain this final setup that I did, but I will also go back to how I started to reach this kind of result. So this is the final result, okay? And basically, this is more like a finished version. But in order to get here, I didn't actually start right away to get to this clean version. I actually made a lot of mistakes as well along the way. So this is the result. This is the random walk. Instead of the turtle is doing it in 2D, but here, because it's Blender, we can do it in 3D space. So we can randomize in all X, Y, Z directions. Yeah, what's going on here? Basically, I'm providing the number, and this is how many steps this we can imagine like a turtle gonna go randomly. So we have like 100 steps. That means 100 points. And for each points, I'm randomly generating this random number between -1 and 1. I can randomize the seed as well, and you can see if I change the seed, the random seed for the X, Y, or Z, the result will change. And the next thing what I did here, I'm joining the list, and then I'm using the Numpy array. Now this is something new in Sverchok actually. This is a Numpy is a Python module that can kind of deal with a big list of numbers in the array. So you no longer think of a lot of numbers as a list, but it's using like a certain special structure of data or array. Basically, this is like a module added into Python at some point, and it's added into Blender, and then Sverchok also have some nodes that's using the Numpy array. I'm using this 1, 2, 3 Numpy array functions. The first one is turning the list into array. The second one is actually the one that's doing the job. This is doing the cumulative sum. Cumulative, that's I think that's how you spell it in English, and sum. That's actually really simple. If you have like a bunch of number, maybe 1, 2, 5, 6, the cumulative sum, and then this one turning it back to the list. This sum functions will generate from this. For example, you have this list of number. This Numpy functions will generate kind of like a cumulative result. 1 plus 1, 1 plus 2, 1 plus 2 plus 5, 8, and plus 6. So it's gonna generate like a cumulative result. That's why in the end, if you put everything together for X, Y, Z data, and using the UV connection, we get this result. So it's really that simple once you understand the logic behind this. I can probably show you using the stethoscope and maybe less of these steps, maybe just 5, for example. 5 steps, and we have this result. Let's not using the stethoscope, let's use the text viewer. And plug this into this and view, and the result is over where is it? Okay, it's over there. This is the steps that's kind of the point or the turtle is taking from the origin. The first one and the second one is and then third and so on and so on. It's kind of like a cumulative kind of point. So how did I get to this point? That's actually the more important process that I want to show you. So I'll hide this. Let's go back to the original version, which is, I believe, this one. Well, this is not the first one. This is actually the nearly finished one. I'll put this on the top. Oh, actually, anyway, this is the one in the middle. Is the first one. This is what I did when I first trying to recreate the turtle thing. I started with a single point, so I kind of imagine, okay, the turtle is at 0.000, and I want to move the turtle in the direction of y. So you can imagine something like this. Let's look at it from the top. So we're gonna ignore the z-axis for now. So we're gonna look at it as a 2D coordinate. The turtle starts from 0, 0, 0, which is this point, and then using Sverchok nodes, we can move it up in the y directions this way. So this is one step, and that's why this is the position of the turtle now. And if you want to move it again, the same, just move it up. We are simply just piggyback the nodes like this. So this is the next node, and then the next node. In the next one, I actually move the turtle to the left here, -1 in x, and I did it twice. So that's why the last position of the turtle is this point. If you notice the difference between the turtle in the pineapple, using the turtle module, we actually tell the turtle to move forward and then rotate 90 degrees, and then move forward and then rotate maybe 90 degrees to that side, and then move forward or move backward. I think you can do that as well with the turtle. So with the real turtle module in Python, you're kind of moving the turtle by rotating and moving forward and etc. So that kind of procedure is actually easier to do in Python. It's not quite clear here unless the node actually does it that way. If there is like a rotation node in here as well, but you can rotate objects, but it's not like a turtle where you kind of controlling the orientation. It's a little bit different. So in Sverchok with a move tool, you're actually moving a single point. You start from there, and you're moving the points based on using this axis, XYZ axis. So you can kind of move it up like 3 units in Blender, or less or more. You're kind of moving it in the vector kind of way. I guess not like forward and rotate, but maybe in the future I will try to set up something that's more like the turtle. So anyway, we kind of able to recreate this kind of a turtle, like tracing the movement of the turtle using Sverchok, and we are doing it in a piggyback kind of way. So, but if we are doing it this way, imagine if the turtle wants to move like 100 steps, we need to do this 100 times. So that's not very efficient, even though it's a kind of easy to understand, but that's gonna be not very efficient. So I decided I try a different method, and in this one, this is actually my second attempt. This is actually the wrong way to do it. But what I accomplished here is actually, this is actually the whole vectors that the turtle the turtle is moving. You can, if you imagine a turtle like a single point in 3D space, and the turtle can move in how many directions? You guess it. Maybe it can move in I don't know. I think I cannot count it exactly. I think maybe 9 times 3, maybe 27 directions. I can't imagine, but it's actually, it should cover, like if you have this is the position of the turtle at 0, 0, 0, and you can move the turtle in all 3 axes, X, Y, Z, and let's say you're moving the turtle a single unit at a time. You can move it in 0, 0, 1, 0, 1, 0, 1, 0, 0, minus 1, 0, 0, minus 1, minus 1, minus 1. Like all these possibilities of directions. Basically, this is what's happening here, over here. So all the directions. So instead of moving the turtle like accumulatively, I'm actually just kind of connecting the points of all the directions of the turtle that's currently making randomly here. So this is the wrong way to do it, but still this is kind of interesting setup. So I put this together, and I'll give you all these nodes set up for you to have a look. Maybe at some point you do want all these arrows. So you can imagine at the moment it's just like a bunch of arrows from 0, 0, 0, kind of all in the same spot, and then I'm kind of connecting the points together. That's why you get something that's resembling like a 3D cube. Okay, that's I don't know, it's kind of interesting. So that's the wrong way to do it. Let me show you the setup. So there's a list repeater here. It's a little bit complicated to explain unless if I create a new file, delete everything. So what's going on just then is like if you use random vector, and I'll show you what's going on here. So random vector is actually generating random values between -1 and 1. And if I generate a lot of them, you see it's kind of clumping together in a spherical kind of way. And so what we did previously, we actually just generating random points within a 3D cube and kind of connecting everything together using UV connection. So this is like all the points is kind of clumping together. If you want to use these vectors, all these random points data, and kind of cumulatively generating the directions for the turtle, we're gonna get the correct results, like kind of like the random walk of the turtle, like the final result. If I'm using line, if I'm not wrong, vector math, if I add this and this together, this should generally give us kind of like a random motion. Kind of, but this one actually has some kind of directions because of the line. This is not totally random motion. Let's go back to our proper setup. Turtle single random walk. So before I reach to this final result, I have this setup. So this is what I did to simulate this piggyback thing. This is the more correct way to do it. So here I'm already using the Numpy to do the cumulative, like a cumulative sum of our list. So in this case, I'm really like manually giving the value of the step of the turtle. So the first one 0, 0, 0, and then the second one 0 1 0 0 1 0 is like representing the directions in the y-axis, because 0 1 0 is like moving it up in the y directions. That's why we have the second points there. And here I'm making only like 5 steps in total. So we have 1 2 3 4 5 points, and for each of the value of the axis, I'm using this Numpy array functions to have this cumulative result. 0 0 0 minus 1 minus 2. I can continue with this if I want. Let's add 2 more steps, for example. So once we reach here, maybe we want to move the turtle down. So moving it down means minus 1 in y. So there you go. And then we want to turn it to this side. That's mean minus 1 in x. There you go. And we can continue with this and kind of making the turtle motion step by step. We can continue. Let's add 3 more steps, for example. And let's move the turtle up. You see, the direction is, we don't need to control the rotation of the turtle. We just specify the vector. Let's moving it up. The next step, moving up, that's mean this 1 in the y, and then moving into the left is this minus 1 in x, and moving it up again in the y. So there you go. That's the 10 step that's the turtle is making in 2D. I can of course use the z-axis as well. So maybe the first step is not doing anything. Maybe the second one I'll move it up. But if I move this up, that's mean, oh, actually the rest of them doesn't move. So this is probably the limitations of our turtle setup. Because it doesn't remember the last position in a, you kind of need to take considerations of the previous value. It's kind of like it's resetting itself, or we are generating the points. Well, actually, no, I was wrong. I didn't use the cumulative. That's why it didn't work properly. Should be like this. Now if we zero everything, there you go. So now it's taking consideration of this. It's already up there, so we don't need to. So now I'm moving the turtle down again in the z-axis and moving it up again. So it has the cumulative effect. So the turtle is already here, and if we see, if I move the turtle down, maybe like minus 1 here, the rest of the position of the turtle will be at the minus 1 position. So this is the cumulative effect. This is, I think, like more correct. File save as. Yeah, so this is the original. You see the piggyback of the nodes, and this is the one after with the cumulative. I think this is more correct procedurally, because what happening here, if instead of listing it one by one, we can really go to the final setup where we actually use a generator to do that, and the rest of them, like the accumulative effects, is kind of like this is like I can kind of join all this together, kind of like the algorithm. Even though this is like really simple algorithm, it's not like if you, one example of a more complex algorithm is when you have 1 point here and 1 point there, and you have all these obstacles, and you kind of asking these points to go there and then avoiding all the obstacles and then reach that in the shortest possible. That's actually a little bit more complicated. We are not there yet. This is like more like kind of like a linear, I think linear kind of procedure. It doesn't have any kind of turning left or turning right based on logic, or this is the simplest you can think of, but still kind of interesting, right? The result is like a kind of the algorithm for pipe. So for the final result, you get this one. I'll give this different color. There you go. And for this one, you can play around with all these generators of number. You can use random number. You can also use vector noise, vector fractal, whatever generator you want to use, and then you can randomize the seed, and you can generate lots of different results here very easily, and you can always bake it each time. And this is an example of some kind of simple algorithm to generate this. But you see, the whole point, I think the concept is if you are a turtle and if you have too much freedom, the turtle is kind of going everywhere like this, right? But even here, we actually kind of giving like some kind of constraints or rules. Hence, the turtles is generating something that's a little bit more interesting, because if you imagine a turtle giving so much freedom, it's just go everywhere and then it might die eventually. But if you give it some kind of rules, the turtle will generate a pattern that's more interesting. So that's kind of the idea. Even if the rule is really simple, so the turtle might actually go in the circle, making a spiral or things like that. That's because of the rules or some kind of algorithm, even though it's really just math function. Sometimes it's on top of math function, we have algorithm or logic or some kind of rules. That the rules thing is the little bit something that's kind of hard, but like Wolfram said, with the simple rules you can create something that's kind of quite complex. And here, this is one example. Maybe this is some kind of algorithm that's happening in nature. I don't know, this is like more like random walk, but I don't know, it's much simpler that we actually can see what's going on. This is when we just tell it to randomly move in XYZ and for the value between -1 and 1. But you can change the rules here and then get a different result very easily and very quickly. So I think that's the point that I want to make here. Hopefully this like a really long video about random walk is very clear. Yeah, if you have anything to add, any question, suggestion, just let me know in the comment section below. Yeah, I guess I'm pretty happy with this, and it's my kind of proper algorithm, random walk algorithm that's actually working, and I understand this everything really well. Previously, I don't actually quite understand what's going on because I got help from the Sverchok developers, but this one I kind of understand it. Even though this is kind of linear, but the fact that we can use this Numpy and kind of accumulate the values is kind of interesting. This is kind of new for me. So yeah, thanks again for tuning in. I'll see you in the next video. Thank you.